All right. All right, I'm going to go ahead and get started just so we can make sure we're on time for the online people who are joining from various parts of the world. So in case you don't know me, I'm Alice DeVivier. I'm one of the Polar Climate Working Group co-chairs. Our other co-chair is Ed Blanchard-Rigglesworth, who I think is on a plane to New Zealand right now, and then Dave Bailey, who's our liaison. And then the Ocean Model Working Group co-chairs are Gustavo Marquez, who should be here at some point this morning, and Ian Grooms, who will be here later this morning or this afternoon. But we're starting kind of the meeting as a joint session, and then there'll be a split this afternoon. So I'm just here to welcome you and give some initial logistics. So the first, welcome to people who are online and everybody here in the main seminar room. The code of conduct we have here, we want everyone to have an equal opportunity to engage online and in person. So I'm going to try to follow any questions that are in the chat, and we have others monitoring that as well. But overall, we want people to be respectful, be collaborative, consider differing opinions, communicate openly, and be mindful of others. If you're here in the room and you need to join the internet, you maybe already figured this out, but there's a UCAR visitor wireless that you can join. You'll have to do a register before you get full access, but that should be fine. And then if you need any to contact anyone during the meeting, I have all these emails here. You probably got them all in your registration, but Elizabeth Faircloth, I want to thank her and the other admins who have done so much to organize all the logistics of this. If you're in person, there are admins sitting at the table outside that you can ask questions to also. And then you can email me or Dave or Ian or Gustavo. All right, so a brief summary of what the structure is going to be like today. So we have joint sessions this morning, and the focus of these topics are on wave-ice interactions, and that's here in the main seminar room. There'll be a break from 10:30 to 11. I know this is a pretty long 2-hour period to go without a break, so if you need to go, just run out and come back. It's mainly because the seminar timing made it a little awkward to try to have a different break in there. So there will be a break between 10:30 and 11, and there will be food outside and welcome and casual chatting before the seminar, which is going to be a remote seminar by Chris Horvat from Brown. And then we'll have lunch. We have an hour and a half about for lunch, and then we'll rejoin all of us together again in the main seminar room this afternoon, where you'll hear more about CESM3 development plans, state of the model, that sort of stuff, and we'll have a discussion at that period too. So we'll have a discussion this afternoon or this morning before the break, another discussion this afternoon. And then at the 3 p.m. end of that session, there will be a break, and then we'll split, and the Polar Climate Working Group is going to move to the Damon room, which if you don't know where that is, you can follow me or Dave or Marika or someone here, but basically you go up the stairs, take a right, and you kind of go around to this nice room at the back of the building. And the Ocean Model Working Group is going to stay here in the main seminar room. And we wanted to let you know that there will be an optional self-pay gathering this afternoon at Southern Sun. Southern Sun only accepts cash. I have been told to let everyone know it's Stout Month, so if you like stout beers, then you will be happy. The Ocean Model Working Group is going a little bit later than the Polar Climate Working Group, but we can all convene there when you're done. I think happy hour technically ends at 5, so just to be aware. And then tomorrow, the two working groups are going to be split again. The Polar Climate Working Group will be in the Damon room again, and the Ocean Model Working Group will be here in the main seminar room. And just a couple facilities comments. There are water fountains around. If you're not from here, try to stay hydrated because of elevation and stuff, and it's been an absurdly dry winter. For food, there will be food at the breaks, but the cafeteria sells lunch, and you can pay with a credit card. And then restrooms, this is a little bit out of date, I found this morning. There are men's and women's on the first floor, so if you go out of the main seminar room, it's a choose your own adventure if you go up or down. If you go down, the men's is on the left, the women's is on the right. And then if you go up there is a single-use accessible restroom if you take a left, and then there's a men's restroom if you take a right. The women's restroom on the second floor is under construction of some sort. And this is the last slide, but just some goals of the meeting. We're having these joint sessions because we want to increase collaboration between the polar and the ocean model working groups, especially on some of these new science opportunities like waves and how they're impacting the whole Earth system. We also want to get community input to inform model development and experiment design in CESM3 and after that release. And we're trying to reduce meeting fatigue so you don't have to go to all of these meetings. The individual sessions by model working groups will be more traditional model component development and community studies or results that are maybe a little bit more just polar focused or just ocean focused. I think everyone got this in an email, but to make sure you know, the meetings are going to be recorded. So, it should be available online later. And in this room, there's power under the seats. In the Damon room, there's power in the center of the table. And then they have now installed these barriers, but they really don't want us to touch this screen. So that was something I had from a previous meeting. So I think that, and this is the last slide. This is if you want to sign up for the CESM newsletter or other CESM communications, we have these links here. And then if you're social media inclined, there are ways to tag NCAR or follow NCAR and CESM, CGD, all of that kind of stuff here. So I think that's it. So without further ado, I'm going to invite our first speaker who is remote. It's Letty Roach. So Letty, one last thing, in those seminar room, when we're asking questions, the ceiling mic should be on. So they're going to let me know in the back when they get turned on. If you have questions, I'll call on you, and then online you can just unmute yourself and I'll let you know when you can speak. But the speaker will have to have a microphone. So, all right, I think that's it. Letty, go ahead and share and take it away.
Hello, can you hear me? You can hear me? Can you hear me? You can't really hear me? Hello?
I can hear you.
We can hear, okay, people online can hear me. Can people in the room hear me?
Online we can hear.
What about in the room?
In the room, we can hear you too. We're good now.
Okay.
And we see the screen. Okay.
Okay, sorry about that. Hi everyone, thanks Naomi, and thanks for letting me join online. I've just got a few slides here to give a bit of an update on ocean surface wave interactions with sea ice in CSM3. Just to introduce this, one of the key challenges in representing sea ice in climate models is that we have this very complicated material with flows of different sizes, spanning many orders of magnitude, and we need to be able to represent this material in a continuum model with grid cells maybe on the order of 10 to hundreds of kilometers. And so most sea ice components in climate models use the sea ice thickness distribution to give some sub-grid scale information about sea ice. So this function G of H describes the area fraction of sea ice belonging to different thickness classes. And it evolves in models according to advection due to a momentum balance, thermodynamics, here represented with a meltal growth function F, and ridging or rafting. So then as a further step, in recent years, a few of us have worked on the sea ice flow size and thickness distribution. So here F of R and H is the joint distribution describing the fraction of grid surface area covered by sea ice with thickness between H and H plus DH, and lateral flow size between R and R plus DR. So that's a radius. And this theory was introduced by Chris Horvat, who's here. And in a similar way, we can write an equation that describes the evolution of this distribution subject to advection, thermodynamics, mechanical interactions, and wave fracture. So I work towards implementing this model in size 6 ice pack. With this implementation, we had no feedback between the flow size distribution and dynamics or mechanical interaction. So the flow sizes are just affected passively by the CI's momentum. What we have updated since those earlier papers is a new wave fracture scheme, and so I'll come to that towards the end. And also just to mention that there are other kind of implementations of this type of approach underway in different models. So I'll show a few plots from a development simulation with CSM3, and here I've used the BHIST 271 configuration. So this has the atmosphere and ocean. Then we have size 6 and wave watch coupled by via the flow size distribution. So this coupling introduces a few new processes. First of all, we have wave attenuation in sea ice. So this is the damping of wave energy by sea ice, which is quite complicated. It depends on the properties of the sea ice, and so there is a fair amount of uncertainty here. But overall, we have damping of high-frequency waves, so you get these quite smooth swells like you see here in this pancake field. And what we've used in the model is the Malin et al. Flow size dependent attenuation scheme. And so this means that we have waves within the sea ice. So at the right, I'm just showing March 2010. The colors are significant wave height. The yellow contour is the 15% sea ice concentration contour. And so if you were to follow a straight line, this is just along the 0-degree longitude, then this is what I show here in the line plot at the bottom, that you have large significant wave heights in the open ocean. These start to decrease as you move towards the sea ice. And then you have this reduction down to 0, but you have some area within what is often called the marginal ice zone, where we have lower sea ice concentrations and we have quite significant wave heights present. Then on the sea ice side, when waves are present, this affects the flow sizes that are formed during this process. And so the idea is that if you have no waves, you would form very large flows. But if you have some wave activity, then you would set an essential limit on the size of flows that can be formed. So if you have strong wave activity, you would form these very small ice flows called pancakes. And we made an attempt to calibrate this with in situ observations. Then in the model, and here I'm just showing October 2013, you see that the perimeter per unit area, so this is really the total area of ice around the edges of flows, a measure of the fragmentation. This is quite strongly increasing in areas where we have ice growth. So this is really a very effective process for increasing the perimeter. We also have flow welding, so we represent this in the model just at the current state, at least, just in a simple way by allowing flows to freeze together according to their geometric probability of overlap by a coagulation equation. And this we also made an attempt to calibrate with in situ observations. And we see, if we look at the representative radius, which is like a mean flow size, the tendency here, again in October, so in freeze up, you'd see this is acting to increase representative radius. And we see that it's effective in the central ice pack, and it can cause, it's really the central process by which large flows are created. We also represent lateral growth. So here, flows are increasing in size. So there's a redistribution amongst the flow sizes towards larger flow sizes, as well as a change in the concentration of the ice, according to the volume of new ice growth in what we call the lead region per time. But this turns out to actually have a very small magnitude in the model, so I didn't include it here. It has very minimal impacts on perimeter and concentration. But then its opposite process, so the lateral melt, is significant. So this is really just doing the opposite, going to smaller flow sizes and also reducing concentration, where we use the same lateral melt rate as would be in the standard model with no flow size distribution, which assumes a constant flow diameter. And we find this has significant impacts on sea ice concentration. And so it's really the main way in which we have a feedback between the flow size distribution and the rest of the model. So this is effective in melting out small flows. So that's the magenta areas on the edge of the ice pack. and will also change the overall concentration and thickness of the sea ice. And then lastly, there is fracture of sea ice by ocean surface waves, which acts only on the flow size distribution, so it's not affecting concentration or thickness. This was described by Dumont et al. As being according to one of two limits. So you could assume that sea ice is completely rigid, it's not flexing with the sea surface, or that it's completely flexible with the sea surface. And they suggest looking at both of those limits and then computing either or, resulting from the largest of those two. In practice, the second one is what got picked up sort of by the community. And so using this assumption that the sea ice is completely flexible. And so this is what was used by Chris in 2015. And then we also implemented in SICE in the later papers. But we knew this was some sort of approximation that we weren't really happy with. And it also gave us some quite large strain values that didn't seem to be very physical. So in some recent work led by Bruno Tremblay, we developed a new approach based on thin elastic plate theory. So now we're not making either of those extreme assumptions, but actually calculating an equation for the deflection of the ice relative to the sea surface that we found we can solve analytically. We recover the both of those extreme limits that are separated by this characteristic length scale with capital gamma. And so the structure of the parameterization is still quite similar to what we had before. We're still computing a strain, but it's having a bit more of a physical basis. And if we look at some of the strain results, this is computed from just sort of idealized simulations with a single flow. Then you can compare the fully flexible scheme on the left. This has quite high strain values, going up to 0.04. We also saw with this scheme that if you have flows of size of smaller sizes, so here the flow diameter is 50 meters, that we have increasing strains as thickness increases, which we did not think was really realistic. But with the thin elastic plate scheme, then we have in this blue line, we have a decrease in strain with increasing thickness. And our flow sizes, our strain sizes are on the order of 10 to the minus 4, which is still maybe a little large, but it's much closer to the kinds of observed values that we saw from, for example, Langhorne et al. 1998. And so this scheme has been coded up and is now active in this CSM3 development version. And it's still kind of active area to keep doing some more analysis on that. And then just to wrap up, just to show that in this historical simulation, there's some indication that these processes might be becoming more and more important. If we look, for example, at the significant wave height, I've just taken a September decadal average from early on in the satellite era towards the end of the simulation. And so you can see that you have these increasing wave heights, both outside the sea ice edge and also somewhat also within the sea ice. So here at the right, I show the difference between those two panels. And you see that you have these large significant height increases, for example, in September around the ice edge. And so to end with some questions, so hopefully with this new capability, we can go some way towards better understanding how ocean surface waves and related sea ice processes are changing and will change in the emerging Arctic and Antarctic, how significant this feedback, so really the main one we're representing is this lateral melt feedback with fragmentation. How significant is that in the fully coupled model? How can we further improve process representation, and how can we compare with limited observations? So then to go towards the discussion in terms of needs or things to kind of put on the table, I think, so that now we've got now that the development version has all of this physics included in it. I think we will need some simulations with things turned off as a baseline to compare against. So maybe simply just having no FSD and no wave ice interactions would be the simplest case there. It would also be nice to have a constrained simulation to compare with observations. So maybe something like a data atmosphere model. And then maybe we would also like to discuss a bit more as a group the output. So I noticed just in putting these slides together that there isn't very much in terms of the wave output. And so just making sure that we have everything sort of turned on that would be useful there. So that's all I have. Thanks again, and happy to take any questions.
Are there any questions in the room for Letty? Not yet. We're saving it for discussion. People are still waking up. All right, we have a question. Alec Petty has a question here.
Yeah, thanks for the great talk, Letty. I guess it is your hope that it also, you can somehow track the size of the marginalized zone, and I know there's different metrics to do that. Do you have any thoughts on that? Like, I guess there's the kind of wave affected definition, and then there's the kind of just more concentration based, and if you've looked at how that's changing with and without the scheme.
Yeah, I mean, I think, you know, there's been quite a few different studies who've used different kinds of definitions, and I guess it really depends what the, you know, which one is appropriate. I think depends on what your aim is. And so I think like moving towards doing some comparison with observations, it would sort of really depend on what observations we're looking at and what we could do that kind of, you know, gives us the closest apples to apples comparison, I think. Thanks.
And we have a question online from Mitch. Do you want to unmute Mitch and ask?
Yeah, sure. Thanks, Letty, for that. It was a great talk. I was just curious how the adding the wave ice interactions affects the computational cost of the model.
Great question. I do not have numbers really very close to hand. I think possibly Dia Zhang has some in her presentation. It definitely is more expensive. The wave fracture is really quite expensive. We did find that moving to the new scheme saved us a little bit in computational costs because you're just not computing as many times. You're not computing wave fracture so much because the strains are lower. So that is positive. But yeah, I think there are others here who can give a bit more quantitative answer to that, perhaps.
Great. Okay, thanks.
Thanks.
I think when we were first estimating this to tell Dave Lawrence, the chief scientist, it was something around like 10 to 15% more expensive of the cost of the whole model, and it was primarily the wave fracture. So Dia Zhang will talk more about that, but I know it's different for different models, and we'll hear a little bit about that later too. All right, so I'm going to introduce our next speaker. We're getting the her talk up. So our next speaker is CC Bitts, and she's going to talk to us more about the wave ice interactions in CESM as well.
Thank you. Really great talk, Letty, and we didn't coordinate enough because I was in the Arctic until Monday. So I'm sorry about that. But I'm going to also talk about recent work in the CESM, and I think I'll just get right to it since Letty already gave a lot of great background and just show you the basic impact versus our old method, which was to just prescribe all flows at 300 meters. And the biggest impact on the sea ice is that it shifts what would be lateral versus basal melt, which was formerly almost entirely basal melt, into about 50-50. And that's because the flows are much, much smaller than 300 meters at the edge, and therefore their perimeter to base area ratio goes way up, and that gives rise to more lateral melt. And when we compare the impact on the sea ice itself, it changes the ice thickness and the ice concentration in expected ways, where it's thinner and less concentrated at the ice edge, especially. But I really wanted to get to our recent simulation. Letty also presented briefly a little bit more depth and show you how it looks. So this is the recent 1850s control simulation and 10-year means here. And what we're seeing is just a beautiful sea ice concentration, and I'm really thrilled to see that after a long development period with some bumps on the way. And this looks great to me. Of course, we're comparing against the modern record here, so we don't expect perfect comparison by any means, but it's in the direction we expect. And the significant wave height, as a result of the wave ice interactions now, you can see the wave height is dramatically different in the presence of sea ice, with strong attenuation by sea ice, of course. But nonetheless, there is still wave magnitude at the marginal ice zone in the edge of the sea ice. And this has these consequences that are dramatic for the flow size distribution. I decided to do one experiment, of course, starting it yesterday, of a perturbation run where I turned off the attenuation in the sea ice. So it's, let me rephrase that. It's completely attenuated in the sea ice now in the second run on in the middle frame here. And it's pretty hard to see the impact on the ocean mixed layer depths by eye because they're already pretty small in the presence of sea ice. But a difference plot shows that the mixed layer depths are really about 50% smaller if we have no wave mixing in the presence of sea ice. Love to talk to oceanographers about better ways to characterize the impacts on the ocean if you can talk to me afterwards. But back to what the sea ice itself looks like, Letty did show the representative flow size radius in the northern hemisphere. Here it is in the southern hemisphere. And of course, she also got the question of how does this compare, or does this give us an opportunity to give a different measure of the marginal ice zone, which is generally known as the wave affected part of the sea ice. And you can see the representative radius versus the sea ice concentration are not mapped one-to-one. And so it definitely does give us an opportunity to have a more faithful definition of the marginal ice zone. I've also shown some flow size distributions here for your information. Really, what we're trying to do is actually simulate this 15 bins of flow size as a probability in each grid cell of occurrence of these different bins. And I did some conditional averaging on the 15 to 18%, 80% concentration, and 80 to 100%. They're not that different. I was actually expecting them to be more different. But one thing you may notice is this large truncation error at the very end where the magnitude goes way up. And that's something we would like to improve upon. So this is the basic CESM3 model as it stands. And I'm going to talk about ways we'd like to improve the flow size distribution. So that basic pattern is also shown here in turquoise from our earlier work. And it was shown versus observations to have some bias. And there's one other model in here that basically is a relaxation to the observations, so kind of gets the right answer better, where we're really trying to do this at a very process-oriented level. So we're basically working on ways to improve. And one thing we would like to do is improve that, bring down that truncation error, but there are lots of other ways we'd like to improve. One is that we're not getting big enough flows in the Central Arctic, just simply because we didn't have a bin size that went very high. So we're going to extend the bounds in the simulations I'm going to show next, which are all improvements on what we have in CESM3. We'd also like to potentially get a better accuracy in the wave fracture that he mentioned. Depends on this new physics that allows the ice to bend, and that discretization is at 4 meters, and flows are now down to 1 meter, so we're not really getting very accurate characterization of the fracture. So we're going to think about how we can do that better. Currently, we don't account for deformation, so that would be like the strain rate on the sea ice itself doesn't cause wave fracture. We've been improving that and taking that into account. We've also been modifying the welding kernel to try to get more, faithful welding. And basically what happens in this model today is that waves fracture it and then it welds back and forth very fast and probably not as observed. What we see in observations is kind of a more steady pattern of the flow size when we look at MODIS images from one day to the next. I don't actually think a lot of this has a huge impact on the ocean. I think we got the basic science right, but well, we'll find out though, I guess, once we really implement these in fully coupled simulations. But somebody asked about the timing and the basic CESM timing. Now, these are just relative values. We calculated about 11 seconds per model day for this discretization at 4 meters. So we thought, okay, well, how does this change if we do a better job at discretizing, just doubling it? And it increased the model time by an order of magnitude. And I don't think we increased the number of processors, right? So that we might have been able to parallelize a little bit better. Anyway, another thing we wanted to do was extend the bounds, and I mentioned that's motivated by something that Gerard's going to talk about next, but it's to better have deformation effects in the Central Arctic, and that also increased the model a lot of times. So we were like, we're being defeated by what we really want to do here, and so we implemented an emulator of the wave fracture process itself, and we did this using a simulation at 2 meter accuracy. So we were able to emulate a more accurate version of the scheme, and then when we do that, the emulator is much faster than even the coarser resolution. So these toasts floating on the ocean here are meant to represent the 12 bins. And what happens in the wave fracture scheme is each bin can fracture into smaller categories or smaller bins. And so say flow bin 11 can fracture, and when it does, its probability of fracturing where it goes is shown here just for some example. And a different example, so this is what we're trying to emulate, this so-called fracture histogram. And this is the work of Gerard, so he will be able to answer all your questions. But what he did was, based on the method that Horvat and Roach also implemented previously for the Horvat and Zipperman wave fracture scheme, we're now kind of repeating something similar for the new Tremblay and Roach scheme. So we have a 2-step scheme where first we have a neural net that asks, is it going to fracture? And if it fractures, then another neural net that is engaged to actually calculate that histogram itself. And Gerard has implemented this in CESM, not fully coupled simulations yet, but at least coupled with waves. And the emulator is doing a fairly nice job at predicting the kind of histograms that the full model physics does. By the way, we only do this for the 6 largest flow bins because those are the ones that are very costly. We just kept the physics for the smaller bins because they're small, and the actual physics is pretty fast, maybe even faster. But the full result on the flow size distribution is really excellent. There's really hardly any difference between the emulator and the physical based model. And that extends to other sort of derived quantities like the representative radius and the significant wave heights. The last thing, how much time do I have? I kind of start another minute. I mentioned that we wanted to kind of adjust the welding, and this is the coagulation theory that Letty implemented from Filbert and Lancelot. And what they did when they did this was to choose a kernel here. The A is the kernel. That was the product of the areas of 2 flows, and we adjusted that to be the product of the perimeters. So that had some significant impacts, and I won't talk too much about it since I'm running out of time, but I thought I'd show just one last video of what this looks like and why I'm frustrated by, this is just 1 month, and basically it just moves the ice edge where that fracturing is occurring and where the welding is occurring so rapidly that it would, if we had an image like the satellite image above, it would just be fracturing and welding and fracturing and welding. Whereas if we look at day-to-day MODIS images, they're pretty stable. So I still think we have room to improve. So with that, I'll just summarize, if I could get my summary slide up and say, I think that we have currently a good model with pretty sensible results. The ice edge looks great. There's lots of ice wave interactions to explore. And I'm also really excited about looking at how this will play out in 21st century simulations. But we're working on improving the spatial heterogeneity in the Central Arctic. We want to implement a dynamical flow size interaction. So we'll have the flow size influencing the rheology. Geraint's been working on that. He'll show some really great results. We needed to extend the flow size, so we needed to speed up the model with an emulator. That's working really well. Finally, I'll just note that I had to originally adjust the wave numerics in WaveWatch 3, and I'm not going to talk about that today because it would bore you to tears, but I'd love to tell you if you are interested. Thank you.
All right, do we have any questions in the room? We'll start with Dan.
Thanks, Susie. I was wondering, do you expect needing to retune any of the parameters if you move to different resolutions in the ocean?
No, I mean, you're saying parameters in the sea ice
Yes.
flow size? No, I really don't think so. I mean, because these flows are at the meter scale. Yeah, I mean, at some point we would have the largest flows in the tens of kilometers, and we could have resolution finer than that. Seems like a bit of a mismatch, but since it's a subgrid scale parameterization, it'll run just fine.
Right. Online? Are you doing that for online?
I can do it for Ed. Do you want to go ahead?
Hi. Yes, hopefully you can hear me. Great talk, Cece. Thanks so much. And I was sort of fascinated by those changes in the ocean mixed layer depth that you showed. And this is a question I think maybe also for Letty. I was wondering if you've looked at the high frequency variability and whether once you have active wave ice coupling, whether you see that sea ice variability go up as you have either big swells or maybe kind of calm seas, kind of in time.
I have looked at that, Ed. I didn't look at it in these simulations since I've only been back from the Arctic for less than 48 hours. So I haven't done it with the most recent simulations, but in our developmental simulations, it does increase the variability in the sea ice. So we have more extreme 5-day anomalies in the sea ice with the wave interaction, sea ice.
Okay.
Well, I wanted to ask about what your thoughts on the wave model resolution. I mean, because in CSM3, we're running a coarse 3-degree resolution,
Please increase it.
Yeah.
You can see this dramatic gradient in the significant wave heights at the ice edge. This is being resolved at 3 to 4 degrees or 3. Fair. Not good enough. So we would like that to be finer. Right now, it's of course being interpolated to 1 degree when it goes into the sea ice model. So sea ice is seeing a finer resolution, but it's super smooth. So please increase it and tell us how. Moment. Oh, sorry.
Well, we haven't, I want to keep us on schedule because we
Yeah.
have remote people, but there is a discussion at the end of this. So maybe some of the questions, David and Moma, can be brought up then. Is that okay?
But it's, yeah. I can do it.
Okay. All right. Our next presenter is online, and it's Dia Zhang. She's visiting us from Europe. So Dia Zhang, are you able to unmute and share your screen?
Yes. Can you hear me?
Yep, we can hear you.
Can you also see my slides?
Yep, looks good.
Perfect. Okay, yeah, greetings from Germany, and thanks for having me here. So I'm Dia Zhang Mojo. I'm a PhD candidate at the University of Bremen, and last year summer I visited Dave Bailey and Marika at NCAR, and we started with this new project, which is about developing a machine learning-based parameterization of sea ice flow parameter for CESM. So Letty and Cici, they already gave the physical background of the flow size distribution. So basically, sea ice flows vary greatly in size, ranging from centimeters to kilometers, and the size of flows is impacted by various physical processes like the melt and growth of individual flows, the flow welding, the flow fracture, and the new ice formation. So why do we care about the size of flows? As Cici and Letty also already mentioned, it's important for the lateral melting. So specifically, lateral melting is parameterized as follows. So the change in sea ice fraction due to lateral melting is defined as the product of the lateral melting rate, the total perimeter of flows per unit area, and the sea ice fraction itself. To give you, to illustrate what the total perimeter actually means, let's take a look at the schematic here. So here you see two model grid cells where the sea ice concentration is the same, but in the lower grid cell, the perimeter is way higher because you see way more smaller flows. So essentially, the sea ice here is more fragmented. So simply put, the higher the perimeter, the more fragmented the sea ice is. So the perimeter indicates how much sea ice is exposed to the ocean at the flow edges, and therefore the available amount for lateral melting. And in previous CSM versions, the perimeter is set to a constant. So yeah, Letty and co-authors, they implemented the flow size distribution, the FSD, which will be turned on in CSM3 by default, which takes into account all the flow size related processes. The problem is that it is computationally expensive. So the goal of the study is to emulate the FSD, so taking into account all the flow size related processes to parameterize the flow parameter. So we want to reduce the computational costs compared to CSM3 where the FSD is turned on and improve the representation of lateral melting compared to CSM3 where the FSD is turned off. So this is the workflow of our study. So first of all, we generate training data from CSM3 outputs, and then we train a multi-layer perceptual neural network, so very simple neural network architecture. And yeah, we use the CSM model output for training the neural network. Then we perform sequential feature selection, which is a machine learning method to get a ranking of the most important input features. And based on that, we develop parsimonious models, so models that perform well with as few inputs as possible, balancing model error and complexity. And the main goal is then to couple the parsimonious, the best performing model online to CESM3. So the training data, so we perform a fully coupled pre-industrial run, turning the FSD on with a spatial resolution of 2/3 degree, and we output instantaneous half-hourly data and simulate 4 years. So the first year is used for spin-up, the second year for the training, and the last 2 years for evaluation. And we use the following candidate variables that are available in CSM3 where the FSD is turned off, namely sea ice fraction and volume per unit area, so from the ice thickness distribution, sea ice velocity, ocean heat content, sea surface temperature, ocean currents, significant wave height. From the atmosphere, we use winds at 60 meters, 2 meter specific humidity and air temperature, and atmospheric ice stress. And our target variable is the flow perimeter per unit area. To give you a physical intuition how the flow parameter looks like, here you see spatial maps and the monthly distribution for each hemisphere. So basically you see that in the northern hemisphere, we have a lot of low parameter values, which represent less fragmented multi-year ice, and then we also have seasonal ice in the northern hemisphere, whereas in the southern hemisphere we have mostly fragmented seasonal ice. Okay, let's jump into the results of the machine learning pipeline. So here you see the ranking of the most important features derived from the sequential feature selection. The most important feature is the subgrid scale ice fraction, followed by significant wave height, then the ice volume per unit area, ocean heat content, and SST. Here you see the monthly root mean squared error for different models. So here I'm comparing the full set model, so the neural network trained on all the candidate variables. SFS3 model is the model trained on the first 3 input features, and then also SFS4 and SFS5 for the other input features. And what you basically see here is that looking at the global RMSE, you don't see significant differences, but looking at the northern and southern hemisphere each, you especially see that adding the ocean heat content improves the neural network prediction during the melting season in both hemispheres. Here I'm also comparing the SFS5, including the ice thickness distribution, and then also only taking into account the mean, so the mean ice fraction and the mean sea ice thickness in each grid cell. And what you basically see here is that the including the ITD is crucial, so for better NN prediction. Now let's take a look at some time series. So I just picked some locations in the northern and southern hemisphere. So you see that the predictions are quite well. Here, for example, you see this sudden jump from low to high parameter value, which is associated with wave fracturing. And this is captured quite well with by the neural network. But what also happens in other locations, you see that the neural network prediction is very noisy, and we are still working on improving that. Okay, online coupling. So for that, I use the CSM3 Alpha 07F tag, simulating only 2 months just for testing. So if you turn the FSD off, you get 5 seconds per modeling day. Turning it on increases the computing time to 1.52, which is about 30% of the whole size model. And then plugging in the machine learning based parameterization, it decreases the computing time by 0.82. And for the coupling, we used AppTorch, which is the Fortran PyTorch bridge developed at ICCS Cambridge. And this is the standard library in the machine learning enhanced version of CESM. So the machine learning based parameterization is faster. So now I already come to the summary. So we see an overall good performance of the neural network using the 5 most informative input features, which are the subgrid scale ice fraction, significant wave height, the ice volume per unit area, the ocean heat content, and the SST. Including the subgrid scale information is crucial for NN prediction. We see that the predictions are noisy, which we still need to improve. and coupling the machine learning based parameterization using FTorch is faster than the FSD. So next steps and ideas. So we also want to include an additional step, which is the neural network classification, where we basically want to classify first whether we have pancake eyes or not. So pancake eyes is represented by very high values, so above 0.7. And if that's the case, then we just assign like a fixed high value. And if not, then we perform the neural network regression. And we do this because we still see in some time series that the neural network is fails to predict these high values. Yeah, and also another idea from the ML people that I got was to train generative models, which takes into account the underlying distributions of the inputs, and that could potentially overcome the noisy predictions. And of course, also evaluating the machine learning-based parameterizations online. So yeah, thank you for your attention.
All right, we have time for a question or two. We have one in the room.
What is the relevance of wave direction for your results?
Wave direction?
A significant wave height does not account for direction. And I imagine that if you have a convergent waves into the shelf, you should have some importance to your simulation.
Yeah. I mean, the only information that we get is the significant wave height. So yeah, I don't know if Letty has an answer to that. Yeah, I'm not sure.
Good question. I saw Will Gregory raise your hand online. So why don't you go, Will, and then after that, we'll move to the next.
Yeah.
Hey, yeah, cool talk, DJ. Can you hear me okay?
Yes, yeah.
Great. Yeah, I was just curious. Yeah, on this slide, actually, you mentioned here that you've got a 4-year training or 4-year simulation with half-hourly input. What was the motivation behind that? I'm just kind of wondering if the noisiness you're seeing is by learning these half-hour snapshots, and if you would reduce some of that impact by maybe still learning half-hour snapshots, but implementing them as like a running mean of those snapshots or something where, you know, over 6, I don't know the timescales of when these things are kind of critical, but I don't know if that would help.
Yeah, so the model time step is 30 minutes. So we wanted to make sure that we really learn like the actual output of the FSD. But yeah, I haven't mentioned it, but for the training, I subsampled the data. So because from each month I got 10 to the power of 8 data samples, which is a lot. So I subsampled them to 1 million per month. So yeah.
Okay.
Yeah, but yeah, we've already thought about taking the mean, but when it comes to practical implementation into CESM3, we were encouraged to use instantaneous data first, and then yeah.
Yeah.
So,
okay.
Yeah.
All right. Cool. Thank you.
All right. Thank you so much, Diajeng. All right. Our next speaker is Geraint Webb, who Cece mentioned earlier. So now we'll hear some of his work.
So yeah, hi everyone. My name's Geraint. I'm a student working with CC. I'm going to describe some more. I'm sorry, can you turn on your mic? Or was it not turned off? I thought it was. Is that better? Thank you. Sick. So I'm going to be talking about my work on a new parameterization describing the health of a sea ice flow and its potential to influence wave fracture. So first of all, we have to ask the question that's been asked a lot today. What is the flow size distribution? And I'm sure we're all learning. So if we look at this observation to the right, the flow size distribution quantifies the probability of finding a flow of a given size over a given region. So if you look at these observations over the Canadian Basin, we have a number density on the y-axis and area on the x-axis. You can see that over this domain, you're very unlikely to find very large flows, but you're very likely to find very small flows. And generally it follows, as we've mentioned before, this power law, except the slope can vary depending on where you are and what time of year it is. And so I'm going to kind of skip over this because we've talked a lot about this, but SICE models the FSD with 12 bins. SICE prognostically models 5 processes that affect the flow size distribution. And Letty did a great overview of these. So new ice creation, lateral growth, lateral melt, welding, which I'm just going to remind everyone is when 2 flows come together and coagulate into a singular flow, and wave fracture. And so what we're going to be doing today is we're going to be introducing another process, flow deformation, and a new tracer, flow health, to try to tackle this homogeneity in the Arctic and from this flow size distribution that CC mentioned. And so what is the mismatch between SICE and observations? As CC did a great job showing this as well. So we have this large truncation in the final bin. The final bin is accumulating lots of flows, and this is occurring because of welding. Flows are welding to the very last bin, and they're all accumulating there. So we get this big increase. And so what we're going to be doing today is we're going to be trying to target these last few bins. And so we're going to be looking at ways that we can reduce the magnitude of this truncation between the last bin and the penultimate bin, or the second to last bin. So the first mechanism that we're going to use to approach this is going to be flow deformation. So here's an example of a flow deforming. So if you imagine that there is a divergent ice velocity field, and you can imagine we have this huge flow on the left-hand side here. And so that is being pulled apart by this divergent ice velocity field into many, many smaller flows in the center of the image. So this very large flow is being pulled apart into many smaller flows. And so Niels Hudder did a lot of work on this. And so he came up with a model that we can put into SICE, a mathematical model, I should say, that we can then implement within SICE to represent this process. So what he did was he took SAR imagery a day before a flow deformation event and a day after the flow deformation event, and then compared how did the flow size distribution change between these 2 different events. And so when you do that thousands of times, you do that lots and lots of times, you can end up with something like this change function, or these observations of change in the top right here. And so this is for many different divergences. So some days it'll be very strong, a very strong flow deformation event, and other days it'll be a very weak deformation event. But as you can see, the general trend is very large flows are broken down to many much smaller flows. And then so what Niels did was he got a mathematical model, he applied this model, and we're going to take this function that he has down in the bottom right, and we're going to put it within SICE. So this function is a function of both the radius of the flow, but also of the divergence in the ice velocity. So how are we going to do this? We're going to have and how are we going to compare this? So the model setup for our little experiment is going to be a bit simpler. It's not going to be fully coupled. We're just going to use the CSM3, but we're only going to couple SICE with WaveWatch3. We're going to use the extended bounds that CC had mentioned. So instead of going from bounds out to, say, 1 kilometer in the default version, we're going to take our maximum radius out to 25 kilometers. We're going to have a prescribed atmosphere. We are, sadly, for many people in this room, going to be using a slab ocean. And we're going to do a 40-year run with an analysis on the last 10 years. And so what does this look like? Well, maybe a little bit underwhelming at first. So in the first column, what you see here is the control run. In the second column, what we're looking at is this with this flow deformation parameterization turned on, and the final column is the difference. And you can see there's a very marginal difference in March in the Northern Hemisphere, but it's not like blowing my socks off per se. And so it's only about 300 or 400 meters, and the maximum size of the flow represented here is 17.5 kilometers. So it's really not doing much. And this is getting at what CC was mentioning. So as these flows are being deformed, they're very quickly being rewelded, often within the same time step. They're just deforming, rewelding, deforming, rewelding. Conversely, when you look at September, so welding depends on it being cold enough to have this thermodynamic coagulation of 2 flows come together. You'll notice that it's actually a lot more negative. So there's no longer this welding tendency overriding the flow deformation. And then in areas where there's a lot of divergence, you can see there's a lot of loss of a lot of fragmentation of these flows. So that was a good sign, but again, it's still not perfect. And so what this looks like when you're looking at the flow size distribution, and when we plot it, and just for the Northern Hemisphere,
And the southern hemisphere, as you can see, that has reduced the truncation between the final bin and the penultimate bin. So it has had an effect, but again, it's not that knockout that we were looking for. So to approach that, we're going to try to use something called flow health to help solve this truncation problem. And I'm going to just tell you how we're going to define flow health. So what is flow health? So imagine you have two flows sitting in the ocean, and they're sitting right next to each other, and they then thermodynamically weld together. So now you have one flow that is now much larger. But at the moment that is welded, you imagine there'd be a very small like ice bridge between the two different flows, and it'd be the weakest at this moment. This is the weakest the flow would ever be. So if there was then a flow deformation event, or if there was wave fracture, you would imagine it'd be a lot easier for this newly formed flow to then break back into its constituent parts again. And so you would also imagine, though, that after a long period of time, they might end up with this like healthy ice bridge between these two different flows. So the flows become a lot more healthy. So this is what we're going to describe. So this would be the most healthy a flow could be, and this would be the least healthy a flow could be. And so how do we represent this mathematically? We represent it very similarly to the FSD. So we have a flux convergence in both space, but also due to thermodynamics, so the flows can move thermodynamically. So if you have an unhealthy flow that then laterally grows, it will be equally as unhealthy the next bin as it was in the previous bin. But if there's a positive welding tendency, that should reduce health. So at the moment that two flows weld together, they'll be the most unhealthy they could possibly be. There's also going to be tendencies that will increase health. So you could have new ice. So you would imagine that if you introduce new ice to the system, it would be healthy, one would hope, by this definition. But also wave fracture and flow deformation would actually increase health, potentially counterintuitively, because say you had two flows that welded together, well, now there's been wave fracture, they've broken apart. So now they're back in their constituent parts, which we're going to define as healthy. There might be a better way to do this, but this is just how we've taken a first stab at it. And then finally, there's a time decay term. So obviously we use an e-folding time about 180 days. And so the flows will heal over time. So what I want you to keep in mind is 0 is the least healthy you could possibly be. 1 would be the most healthy. And we're just going to look at grid cell averages here. So what our climatology looks like. So if you look at March in the Northern Hemisphere, in September in the Northern Hemisphere, so you look at March, you can see that flows are generally very healthy, where it's like perennialized, where it's thick multi-year ice straight north of Greenland and the Canadian archipelago. So this way it'd be most healthy. There's less welding, whereas areas where there's lots of welding in the marginal ice zone, so you can see there's very dark light colors. If you can follow my mouse here, you'll see that that's because the waves are the flows are constantly being fractured by waves, and then they're re-welding, and they're being fractured by waves, and then they're being re-welded. And then so likewise, we can see this in September in the Northern Hemisphere. We can see similar things going on. So it's actually a lot more healthy, which you might be thinking, well, it's September. That doesn't sound correct, but it's actually just because there's not so much welding going on, so there's no way to reduce health, but there's a lot of wave fracture, and wave fracture is a tendency increasing health. So that's why it's kind of a little bit counterintuitive here. At the very, very edge, you'll notice that it's always healthy, even in the winter. And so this, you can imagine that these are flows that have been evected out into warmer water. So there's less, there's no longer the welding tendency, but there is the wave fracture. So cool. So that's what it looks like from a climatological perspective. And then so why even make this like big metric and this big tracer? What's the point? Well, it's because we're going to try to amplify both wave fracture and that flow deformation I just mentioned. So wave fracture at the moment, there's a critical strain. So there's a point at which when we calculate in our wave fracture scheme, that the flow will fracture into many different parts. But what if we could instead, if we had a very unhealthy flow, reduce this critical strain? And so so imagine this was the healthiest the flow could be, and it would not be fractured by the stream because it does not breach this critical strain threshold. But then if we reduce that, because you had the most unhealthy a flow could possibly be, it would then be a lot more likely to fracture. And so we choose for just a good first pass, we just make it 10% of the value. So so we reduce the critical strain by to 10% of its original value. Likewise, we increase the flow deformation by about an order of magnitude with another feedback, and we also reduce ice strength. So this is the first time that FSD has been connected to the rheology of the model directly. And so when we do that, we get some somewhat interesting results. Again, we still have truncation in many of the seasons, but you'll notice in September in the Northern Hemisphere, we've actually reduced that. You'll also probably note that it is not following a perfect power law, so there's definitely more work to be done. But it is a good first approach at seeing what happens and how important welding is currently in our model, at the very least, in dictating this truncation error. And so how this looks like in terms of the representative radius as well is there's large decreases in the representative radius in all seasons. So if you look in this first panel in March, Northern Hemisphere, you might actually be able to start to see there's actually some gradients. Whereas if I was to compare to without using this health feedback, it would just be a very homogeneous, homogeneous world of uniform flows. And so you can definitely see that in September in the Northern Hemisphere. Likewise, we have pretty much uniform decrease in representative radius. And the only time we ever have an increase, you might be thinking that's a lot of red, is because we reduced the ice strength. So now the ice is more likely to advect, and it's just moved to a place where there was not that large flows in the past, and now there are large flows because they've just been advected that way. But yeah, and with that, I'll end future.
Do we have questions in the room or online for Grant?
Chris.
Oh, that might have been a clapping. I don't know. Chris, did you have a question?
I did not. That was a attempted clap. Sorry.
I can have one. So there is the concept of damage, which is, I think, the opposite of health. Right, and they write it as a prognostic variable in that model. Would you be able to do that too? We keep track of health or in size.
Yeah, at the moment, we've only kept track of it for the 5 tendencies, but you could keep track of it for something like damage. You could also do it for like if there was other thermodynamic effects that would also affect it, but you could do it on
for the time, right? And then there's healing properly and all these things.
I haven't thought about that very well.
Yeah.
Thank you.
David?
I was wondering if you've thought about basically other processes that join flows together. So particularly ridge formation
Yes,
at the edges of flows.
Yeah, so this is something we've thought about. So at the moment, it's basically we're assuming that this is how flows well together, and that first of all, obviously there's not like a bunch of pancakes that then come together and make one giant flow, but also not like ridging or like rafting. But that is something that we have considered and something that we could include, but it's not actually currently included in like the welding parameterization. But if you were to include it in the welding parameterization, this is just taking the tendency from that. So you could change the welding parameterization as much as you wanted. You could include ridging or rafting, and then you could still have this metric coming out at the end. It'd be quite, yeah.
Last one, Nguyen online. Do you want to unmute?
Sure. Hi, thank you. So my question is about the first comment you have here. It said you use observation to constrain the model. My question is because the flow size is so variable in terms of both spatial and the temporal scale, where your observational data source come from?
And that is a great question, and that's why it's in the future work section. That's what I would like to work out and do in the future. Would be to work that one out. Yeah. But so, no, I haven't used observations yet. It was just a first pass, just like having a go at putting the parameterization in, and then we're going to come back and do some observational work in the future.
So you were thinking it's like more in situ or use remote sensing. So what's the data source possible coming from then?
I mean, ideally it'd be remote sensing, but I mean, it just depends on what's available. And I think this is going to be the next part of our project.
Okay, thank you.
Yeah.
I think that'll be a good thing to talk about too. Like, what do we use to ground truth waves and ice and stuff like that? All right. Thank you, Grant. So our next speaker is Erin Thomas, and she's going to talk to us about waves in E3SM.
Okay. Awesome. So we're gonna switch models here, but there is a lot of overlap between the work that I'm doing in E3SM and the CESM model. We're using the same wave component, and we're using IcePack, so the same sea ice thermodynamic column model. But this is going to include a little bit more than just wave ice. It's going to be an overview of the way that waves are coupled into the full Earth system model. And so we'll do a little bit of an overview of how waves are coupled in, what is the recent developments, talk a bit about the mesh that we're using, which is quite different than the CESM, and then some ongoing efforts and future plans. So quick overview. So E3SM is the DOE flagship model. It has an unstructured mesh in most of the components, especially the ocean, the sea ice, and the wave component. You can see an image here. The little blue hexagons is our low resolution ocean and sea ice mesh, with the black triangles being our new wave mesh overlaid on top. We have Antarctic ice shelves and ocean flowing underneath the ice shelves. And really moving forward, the target effort for E3SM is going to be focusing on AI applications and shorter timescales, so more seasonal to decadal prediction. So our current capabilities in E3SM, the new version, version 3, it's fully coupled, but it also now includes a fully coupled wave component. So we're using WaveWatch 3, just like you all. And we have wave sea ice interactions. So that's my area of interest. But again, we'll focus on an overview of how waves are coupled in to all the other components as well. We, again, are using unstructured meshes, which is nice because it's capable of regional refinement around any areas of interest. And so polar regions, for instance, is one of the areas that we often regionally refine. And then for waves, we generally regionally refine around coastlines and shallow regions. And so again, here's our unstructured mesh. This is our low resolution or our standard resolution in version 3. The blue hexagons is the ocean and sea ice mesh, and we're reaching down to 30 kilometers. So this is our low resolution mesh. Again, 30 kilometers throughout the Arctic. And we exactly match in the wave model the mesh resolution along the coastlines. And so here's a bit of a zoomed in version off of Alaska to see what the coastline looks like in both of our meshes. And so we're interested in how waves impact the full climate system. And so we're interested in wave ice interactions, how waves interact with the ocean through mixing and Stokes drift and Langmuir turbulence, as well as how the waves feed back to the atmosphere through turbulent surface fluxes. And we've included all of these processes in E3SM version 3. So I'll break this down by how waves are coupled to each component separately, but in terms of how waves are coupled to the atmosphere and the ocean, one of the ways that we could view this also is how they are momentum coupled. But I'll just break it down in terms of each component separately. And so the wave atmosphere coupling, in terms of what's physically being passed back and forth, we have winds and temperature being passed from the atmosphere over to the waves, and then roughness length being passed back. And so generally the default version of E3SM, we use an NCAR-based Large and Jaeger surface flex scheme. And there's no way to couple waves in this default setup because the surface drag coefficient is based purely on 10-meter wind speed. And so one of the options that we've experimented with in version 2 was switching to the core turbulent surface flux scheme. This would allow for wave coupling through the Chernow parameter. However, this flux scheme is not consistent with our default setup, which is the NCAR-based scheme. And then also the turbulent fluxes over sea ice surfaces is based on the NCAR scheme as well. So overall, this was not really how we wanted to move forward with wave coupled to the atmosphere. And so what we've done is created a modified NCAR turbulent flux scheme that allows for wave feedbacks by calculating here in the schematic on the bottom. We're passing Z naught, that's the surface roughness, from the wave model up to the atmosphere, where we calculate CDN, so the drag coefficient, the neutral drag coefficient, as a function of Z naught from the wave model itself. And we then iterate through to look for what U star is, so that's the flux calculations there, and then so that affects the tau, so the surface drag on the waves itself. So we've got two-way coupling between the waves and the atmosphere. So moving on to how the waves are coupled to the ocean, we're doing this with boundary layer depth, currents, SST and SSH being passed from the ocean up to the waves. And then the waves are passing back significant wave height, Stokes drift, peak direction and frequency, as well as some stresses. And so that's where this full momentum coupling plays in with the way that the waves are also coupled to the atmosphere. So we'll go with the mixing first. And so we're partitioning the Stokes drift values as calculated in WaveWatch 3, passing those partitions Stokes drift over to our ocean model. That's called MPass Ocean. We then are reconstructing the full depth profile of the Stokes drift in the ocean, and we use that reconstructed Stokes drift to estimate a Langmuir enhancement factor. In terms of the momentum coupling, and again, this is related to how our waves are coupled to the atmosphere. Again, the default setup with no waves, of course, is that the atmosphere stress is equal to the ocean side stress. But when you have a wave component, this isn't actually true. Some of the momentum imparted on the ocean from the atmosphere is lost to the wave component through the generation of waves. But also the waves themselves can impart a stress on the ocean, and we're now accounting for all of this. And so you can see in terms of the full momentum coupling, it's related to how tau atmosphere is coupled to the waves as well. All right, so maybe a little more relevant for this group is how the waves are coupled to the sea ice. And so we're using, again, WaveWatch 3, same sea ice column physics as CESM uses as well. So we're coupling with wave height and the 1D wave spectrum, and then ice fraction, ice thickness, and the ice flow diameter as calculated from IcePack. And so luckily, I am not the first talker today, so all of this has been presented before. Very nice overview from everyone who's already gone. We're using the IcePack column physics and the flow size distribution included in IcePack, and Letty gave a really nice overview on all of this earlier. The braking scheme is based on the Horvat and Zipperman and Roach et al. Methods. Very exciting to see the new fracture scheme coming out soon, so I'm excited to read that paper. And so sea ice flexes with the height field and breaks if the strain is exceeded. And then the wave attenuation scheme that we're using is based on the Malin et al. 2021, so the same scheme as CESM is using, where wave power is dissipated due to sea ice. All right, so just a quick summary of all the results here. So we've got about 65 years now of the fully coupled wave ice run, but I'm going to break this down into two components. So we ran a control run with no waves. We ran a run where the waves were coupled only to the atmosphere and the ocean. And then we ran a third simulation where the waves were coupled to atmosphere, ocean, and sea ice. So we could isolate the impact on the climate due to the wave ice interactions. But first, before we look at the wave ice impacts, we're going to look at the role on the climate system from the wave ocean atmosphere coupling. And generally, global mixed layer depth increases as we would expect because we've got Stokes and Langmuir effects now. This generally increases or decreases the temperature. So we've got increased mixing leads to cooling. And then this has an impact on the sea ice. Here we're just looking at the northern hemisphere. And the impact of the wave ocean atmosphere coupling is the cooling and mixed layer depth processes generally increases our sea ice area and thickness, although this is just the concentration that we're looking at. And so when we add wave ice interactions on top of all of that, so on the left here, we're looking at what we saw in the previous slide. So this is the wave ocean atmosphere coupling effect minus the control run with no waves. And then on the right-hand side, we're looking at the wave ocean atmosphere ice run minus the wave ocean atmosphere. So we're really isolating just the impact of the wave ice coupling on the full climate system here. And generally the effect that we're seeing is that the wave ice coupling counteracts the impact of the wave ocean coupling, and this would primarily be due through lateral melt. And so the increase in sea ice area that we get through cooling and mixing effects from the atmosphere wave ocean coupling is negated by increased lateral melt through the flow size distribution and wave breaking that we get in the fully coupled system. Here's a quick look at what's going on in the summer hemisphere. And again, we see very similar patterns down here. We see increases in ice due to the wave ocean coupling, And then when you include the wave sea ice interactions, generally it counteracts the impacts of increased sea ice due to wave breaking and the lateral melt. All right, so quickly, some of the ongoing efforts and future plans. Department of Energy is just ever increasing resolution on us. And so here again is our standard E3SM V3 standard resolution in the Arctic. It's roughly 30 kilometers or so. And we're moving towards an even higher resolution where we can't even discern what the grid cells are on the right-hand side there. So in the Arctic, it would be down to more like 6 to 18 kilometers. You can have a guess at the impact on the wave cost if we go there. Also, not just in terms of ocean and CS resolution, we're moving towards a 3-kilometer cloud resolving atmosphere. This is called SCREAM. And because of all this increase in resolution, there's a massive increase in cost. And so AI and machine learning applications are also a really big focus for us moving forward. So here's an example of what we're talking about. And so this is our standard resolution, fully coupled E3SM simulation with waves. And so it turns out waves are almost equal to the cost of every other component combined. And so one of the things we're really trying to do is reduce the cost of WaveWatch. And so we have done some work on this to isolate what part of WaveWatch is really expensive. And so here's sort of a cost tree. It turns out there's only like a few source terms within WaveWatch that take the majority of the cost. And so what we're doing is trying to emulate individual source terms. And so one of our postdocs, Olawale, this paper was just recently published, so I could get you the link if you are interested in reading this in more detail. But what we're doing is emulating the nonlinear wave interactions, which is one of the more expensive terms. There's 2 ways the WaveWatch simulates this: an approximation, which is what most people use. That's called DIA, but there is an exact term. And so what we try to do is train an emulator on the exact methodology, which is very expensive, to see if we can get the speed of the approximation method. And generally, I won't go too much into detail here, we are successful at that. And so we are getting about the same results in terms of, this is the RMSE of wave height and the peak wave period. And the RMSE is very good for the emulator minus the exact. And so we are getting very close to the approximate, we're getting very good results emulating the exact methodology at the cost of what the approximation methodology takes. And so we're really excited about this. These are all offline results, but we're moving towards online simulation of this as well. And so with that, I will take any questions, and sorry for the very quick overview of all the ways that waves are coupled into E3SM.
We have time for a couple questions.
Nice to see that all these things come together, right? And not surprised that WaveWatch is that costly.
Yes, well, did you see our mesh that we're using? It's, you know, very high resolution, and that is very hard to counteract. So we're really looking forward to emulating the wave component.
Yeah, I understand that. The question is, if you do like the successful replacement of the spectral fluxes, like this part you showed last, how much does it bring down the cost?
Good question. I don't have that. The timing would be about the same. So in terms of like, one more, this cost. So this WaveWatch simulation is using the approximation method. And so we wouldn't actually be improving on this. It's about the same. We would get more accurate results. That's the difference. So you're getting more accurate wave simulation through the emulator at the same cost.
Does the accuracy impact your climate responses?
Don't know. We have not run this yet. That's a great question.
I wouldn't guess so.
I don't know.
All right.
Nice to see.
We have a question in the chat, and then I'll go to you, Ed, and then we'll switch. So, Katerini, could you mention which linear enhancement you used? Did it account for wind wave misalignment?
Ooh, that's an excellent question. I did not implement the Langmuir coupling. I will have to get back to you. Could you send me an email? My email is in the top corner, and I will look this up for you.
Yeah, I will. Thank you very much.
Thank you so much. Yeah.
All right, last question, Ed.
Hi, yeah, thanks for the great talk. I was pretty fascinated by the results when you couple the waves to the ocean, right? That you got the deeper mixed layers,
Yes.
but you actually got cooling and more sea ice, and I maybe would have expected the opposite. But I wonder if is that a response to the local changes in mixed layer depth in the polar regions, or could it be a remote response to, you know, maybe lower global temperatures as the global mixed layer depths are deeper, and that just makes the polar regions colder?
That's a great question. I haven't looked at whether it's a remote or local balance. I will look into that. These results are pretty recent. So yeah, great suggestion. I can't speak to which it is.
Okay, thanks.
We do see generally global changes in the climatology, and I just picked a few of the figures to highlight here for you guys, but there are a lot of changes. So I wouldn't be surprised if there's a remote component to this, as you suggested.
All right, well, thank you, Erin. So we're going to move to our last talk, which is remote. Noah Day is going to talk to us about the Access OM3 model, and it is almost 4 a.m. in Australia, so thank you for being with us at this time. And you should be able to share your own screen.
Noah went back to sleep.
Sorry, bear with me.
Great. And we can hear you okay in the room. Oh, we're in the infinity mirror.
Yeah, sorry about that. Is my screen coming through now?
Yes, it's not presenter view yet, but I'll let you know if it. There we go. That looks great. Thank you.
Okay, perfect. Hi everyone. My name's Noah Day. I'm a postdoc at the University of Melbourne, and I guess my research interests are in particularly the marginal icene, which we've had a great introduction to already in this session. So I can probably skip over this slide as you're all familiar, but essentially I'm going to refer to the marginal icene as the area of the sea ice cover where waves are interacting with the sea ice predominantly. So in this diagram, we've got waves coming in from the right-hand side. The sea ice, due to its physical properties, will attenuate that wave energy, and then that results in the sea ice determining the extent of the breakup. So we have this feedback since fractured flows are weaker than continuous flows. So the sea ice and the marginal icene and the waves are intrinsically coupled. So what we're trying to do is represent these processes at still quite a coarse resolution, so at 1 degree horizontal resolution at the moment. There's a project led by Alex Fraser from the University of Tasmania, where we were able to capture Antarctic miswidths derived from satellite altimetry. So we've collected 10 years of data. So this is circumpolar and Antarctic miswidths, where the miswidths defined by the distance in which the waves penetrate the sea ice. In this study, I guess one of the findings of the study was that the seasonal marginal ice zone width, which I'm showing the dark blue here, is both highly correlated with the incoming significant wave height. So that's the significant wave height right at the ice edge, as well as the location of the ice edge. So this led us down the path of trying to, I guess, explain these relationships or the causal chain. So we completed a modeling comparison. So we took those observations and then just compared it to a super simple sea ice model. So this is just standalone Sci6, and then I included a wave ice propagation module, just so we're taking in the bulk wave parameters at the ice edge and then propagating them through the ice cover to enable breakup. With this, despite the oversimplified physics, we were getting really good agreement between both the modeled wave penetration and the observed wave penetration distances. The caveat or the flaw with all of this, though, is since we're using such a simple model, the key processes that we aim to understand still remain very poorly constrained. So to address that, we're developing a three-way couple model between the ocean, sea ice, and the waves. And here it is. Well, it's still very much under development, but Access OM3 is an Australian ocean and sea ice model, with 3 being the third version. So in the past, the Australian ocean sea ice models just relied on those 2 components. And we've introduced WaveWatch 3. So we've got coupling between WaveWatch, SciSix, and MOM6. The relevant coupling submodules that I'm interested in are related to the waves and the sea ice predominantly. So as it's been already highlighted in the previous talks, we've got this flow size and thickness distribution, which will take in the wave energy spectrum and then fracture the sea ice. And then WaveWatch 3 will resolve the wave attenuation depending on the mean sea ice properties. So we're also using that Malin 2021 attenuation model at the moment, since that depends on both the thickness and the flow size. But we're also experimenting with a couple other attenuation models. And then for the wave-induced mixing and the Langmuir circulation, we're currently using the KPP mixing scheme in MOM6, and then enabling an enhancement factor to take in the impacts of the waves. So after running that model, are we getting any better agreement with our observations? So here I'm showing the MIS width again. So the observations are in the gray, and then I've overlaid a rolling average. I think it was a 30-day rolling average just to denoise the data a bit. And then the model results in the orange, and here the MIS width in the model is just the distance of ice cover until the significant wave height drops below a specific threshold. But I will mention that although that threshold's kind of arbitrary, our correlations still hold with varying thresholds. So the thresholds kind of determining the magnitude of the MIS width, but we still get this relationship. And we seem to be, getting quite good agreement between the two. For context, using that simpler model that I mentioned earlier, that we were running at a 1/4 degree resolution, we got good agreement in the climatology, but we weren't getting as good agreement in the time series. So this has motivated us to complete this analysis. And now we're getting an R-squared of about 0.7, which we're pretty happy with, even though we're at 1 degree resolution. So we don't have too many model grid cells per longitude to resolve these marginal isotone widths. So we can further analyze these comparisons between the observations and the modeling by extending both time and space. So there's a lot going on this figure, so I'll go through it quite slowly. On the left-hand side, we've got the climatology from the observation. So we've taken every data point from 2013 to 2023 and then gridded them to create this heat map where we've got the seasons on the y-axis and then the longitudes around Antarctica on the x-axis. I've got the corresponding plot taken from the model output, averaged over the same time period on the right-hand side. And then the line plot on that furthest right column, that's the circumpolar average marginal icosahedral width. So that was basically what I was showing earlier. So firstly, with that, we're still getting good agreement as we were seeing with our standalone SICE models, so that's reassuring. And then the two plots up the top is, so the line plot is the temporal average, so we can see the variations at different longitudes around the Antarctic coastline. And then I've included a map of Antarctica just as a reference point, as we've got some key geographic features around the coast. So I'm just going to step through each of these, I guess, segments bit by bit. So firstly, just looking at the second half of the year. So this is when the sea ice is transitioning from winter to summer. So we're including the sea ice maximum and then the start of the melt season in this time period. And we're seeing really good agreement between the observations and the modeling. So the maximum mist widths tend to be pretty similar. We're getting, I guess, some of these vertical lines, so some persistent narrowing or widening of the mist at certain longitudes. And then that's reflected in our circumpolar average, where the mist widths and the observations are quite similar. Moving to the first half of the year, so from January to June, the marginal icosahedral is much more variable, and we get quite a lot of areas where the marginal icosahedral is super narrow, so probably only one model grid cell at this resolution. This is particularly the case on the eastern part of Antarctica, so you can see the strong signal in the model. And that's because there's just so little sea ice around those longitudes that consequently there can't really be a marginal ice zone without any sea ice. The signals in Western Antarctica are much more varied. So we get our annual, I guess, maximum and minimum occurring at similar times around that region. And then looking at our circumpolar average, we're underestimating the marginal icosahedral width at the sea ice minimum in February, and then we're overestimating it during the peak growth season, so heading into May. I'm still disentangling why this might be the case. By looking at sea ice extents for Antarctica in our model, we seem to be overall underestimating them compared with remote sensing. Why we've got this bias is still an ongoing problem that we're trying to diagnose. So another thing we can look at is how this breaks down longitudinally. So in the eastern hemisphere, we're generally getting that strong agreement I was mentioning earlier. So there's very little to no marginal ice zone in the summer months, and then it becomes quite wide during the winter. And by averaging over time, we get really good agreement in these in these average mist widths for around that coastline. So it seems to be much simpler to model in Eastern Antarctica, whereas in Western Antarctica is much more complex. So our agreement's not nearly as good. And my thinking at the moment is that a lot of this is impacted by the Western Antarctic Peninsula, which is next to the Weddell Sea on the map, and the tip of South America. So I'm thinking as these swell waves are propagating around the Antarctic sea ice, that they've been constricted here and on the western side of the peninsula, that ice is really exposed to wave energy, whereas on the eastern side, it's shielded from that land. Yeah, so that's why I think we're getting this kind of dark, persistent shading in both our observations and in the model at around maybe 60 degrees west. Just after that point, we then get some of our widest marginal ice zones. So there's the Weddell Sea seems to be super sensitive to waves, and hopefully when we get to 1/4 degree, we can resolve that area a bit better. So just on what we're working on in the future, so I think just about every talk's mentioned the cost of wave-induced breakup and waves in general, and we're seeing similar things. So from running SICE in standalone, is costing us about 2 hours of wall time per model year. When we turn on the waves, it's gone up to about 12. I've been experimenting with using some known distributions in place of solving the fracture histograms, and that's really sped up the model. But it does have the trade-off of losing some of that physical detail that we have in the current model. Our WaveWatch 3 component is also really expensive, as Erin mentioned in her talk. So that's been our current bottleneck for moving to a 1/4 degree resolution. Anyway, that's it from me. Thanks everyone for listening. And if you want to reach out, my email's here.
Do we have 1 or 2 questions for Noah specifically? So I'll do Letty online first. Go ahead, Letty. Maybe we can not quite the middle, there we are.
You're using for the known histograms, I'm curious. For the wave.
That was very quick. Did you hear it okay
Sorry,
now?
What am I using for the known histograms? Yeah. So I've been experimenting with both power law, but I think what might be more realistic is a log normal distribution. So this is kind of going off of Fabien Montiel's work. All this work's very preliminary, but I'm playing around with setting the parameters of that distribution to things like the characteristic flow size.
All right, do we have any in the room? If you can stop sharing your screen, Noah, I'll put up some topics. And then when I introduced myself, so I'm Alice, I'm the Polar Climate Working Group co-chair. Ed, if you're still online, can you just turn on your camera and wave to people so they know who you are? And then Gustavo, maybe in the room, you can wave so everyone knows. This Gustavo, he's one of the Ocean Model Working Group folks, and maybe Ed's not online anymore. Okay, so
I'm online.
Oh, you are. There he is. So there's Ed, the other Polar Climate Working Group co-chair. Feel free to email any of us if you have questions about the session or anything like that. And Gustavo is coming up here. So we wanted this just to be kind of a discussion period where our communities can talk about kind of things we want to look into, coordinated experiments. I added some things to this slide based on what Letty added in her talk, or things that came up, like machine learning emulation came up multiple times. But I was going to have it kind of be an open discussion for the next 20 minutes. Does anyone want to start out?
So I think, we've seen experiments from other groups that are running with waves, and I think it would be nice maybe to have some coordinated experiments across our groups. I mean, like the experiments that Erin showed with looking at the wave impact, the waves in the ocean, the waves in the sea ice, and kind of piecing apart the different impacts of waves in the climate system. I think those would be nice experiments to run with CESM3, and maybe then we could compare across models and see where there's consistency or not. And I'll throw out another set of simulations that I think would be interesting. I think it would be interesting to see how the waves impact initial value predictability in sea ice. And Ed mentioned, Ed asked the question of, do you see more high frequency variability in CC? Said yes. And I'd be interested to see whether that impacts the initial value predictability that is simulated. So coordinated experiments along those lines would be nice too. Letty?
Kind of just to add on to that, yes, I think coordinated testing for the parameterization development would be really good, maybe just to make sure that we could sort of maybe agree on a bit of a framework so people are doing similar tests and that we're comparing against the same baseline, because things are developing. So I think if we want to show the impact of adding in new processes, that we're kind of doing it relative to the same base state.
Go ahead.
Ed? Go ahead, Ed.
Yes, on that note of coordinated experiments, it seems, like everyone's mentioned how expensive these simulations can be. And so people, are often running kind of shorter simulations, whether it's a few months or a few years. So at least coordinating using the same time period, right? Like if you're forcing it, or maybe if you're running it in like with an observed atmosphere or like observed wind field or waves from wavewatch 3 to use the same time period, so that at least you're comparing apples to apples.
You should also then check the switches of wavewatch itself, right? Because they interact with the attenuation scheme, which is a little messy.
Chris Horvat?
Hey, sorry, I can move you off my second screen. Yeah, I wanted to add that we had a meeting over the summer about wave ice coupled modeling, and we kind of had a plan to set up a set of experiments, but I think as I led that and did nothing with the resulting proposed work, it'd be a good opportunity to kind of revisit the set of planned experiments that we were talking about, especially with the PCWG. So I can't be there today, but obviously would love to hear if there's a plan to do coordinated experiments, especially between DOE and NCAR.
The second that we turn on more diagnostics, because I was just looking in the ocean model and I couldn't find anything that really isolated the wave mixing effects other than just the mixer. Maybe I'm missing it, but I'd also be interested in an oceanographer explaining how it's working. Mom, because I used to have a clue in POP, but now with Mom I don't.
So we are saving now, as of maybe a month or so ago, a bunch of ocean wave fields, significantly high. I think peak period. Not only things that get passed between the couple within the coupler, but also additional wave fields. Unfortunately, WaveWatch output is not straightforward, so we had to do via coupler history file, and thanks to Alper for doing that. And then in terms of the feedback on the waves on the mixing, we are saving within KPP now there is this can save the Stokes velocities that are used in KPP, and then the new parameterization that Theo coded up. So it's large 2021. There's three kind of components that are coming in. Two of them are related to waves. There's a lot of details. I don't know all of them. I will touch a bit on my presentation, but we'll write them up in the description paper with the help from Village.
Yeah, making sure in any coordinated experiments that we have them on, some of these fields on, even if they're not default CESM3 fields, partly just because when you run CESM, it has so much output and stuff.
Yeah. Did you say it's in the coupler?
The way we're saving wave field is via coupler history files, but it is a unique file for the wave coupler history files instead of being merged with all of the other stuff. And it's daily snapshots. Daily averages. Daily, thank you.
In our standard runs?
Yeah, now is out of the box as of Alpha 07G, I think.
This is more of a question for Aaron. I thought that DOE or E3SM has a rewritten new version of WaveWatch 3.
No, so I guess maybe you're thinking about our sort of longer term plans. Our long-term plans for the ocean component is actually to embed our sea ice component and ocean component and wave component all into one.
No, I talk about what Luke was trying to do. I believe Luke was saying that they have rewritten WaveWatch 3.
No, we have not.
You have not, okay.
I would love to, if you want to work together. I'm not sure I'm qualified, frankly, to rewrite a wave model. I'm a coupled modeler, but I very firmly believe WaveWatch is not the right tool for the applications that everyone in this room is trying to use it for. And we desperately need a new climate wave component.
I'm going to go to the topic of resolution. I mean, definitely you see improvements in the resolution that Aaron showed and also NOAA, I mean, running at 1/4 degree and stuff like that. But the expense of WaveWatch is just so crazy when you go down to those resolutions. And that's why in our standard CSM experiments, we're only running WaveWatch at 3 degree resolution. So I love some thoughts, suggestions on a compromised resolution and ways that we can maybe improve the performance of WaveWatch, because I'm sure Dave Lawrence would be very excited if we told him we were going to triple the cost of WaveWatch in the model. So just some ideas and some thoughts on that would be wonderful.
I have a question about the wave spectrum in WaveWatch, because as we go to higher resolutions, at some point, the model probably will not be able to resolve that things so well. So does it make sense to go to such a high resolution?
We are running higher spectral resolution than the CESM component.
Yeah, we've got 25.
I mean, like spatial resolution, but just because I've seen like these wave spectrums, and sometimes they do not improve if you improve spatial resolution.
Oh, okay. Yeah.
So for long-term improvement, I have a plan.
Yeah.
Model, I still want to do that. For short-term improvement, it's still unclear to me how much of the cost is actually the running of the model itself and the transfer of spectral information to the coupler. And the only reason why this coupler needs spectral information is because of your wave fracture scheme, which is also the expensive part in CSM. So I would recommend stop transferring spectral information and go with the moments and figure out a wave fracture scheme that sits on moments. So
We've tested the cost of coupling, or I can't speak for CESM, only for E3SM, and coupling, we couple 36 wave frequencies instead of the 24, 25 that you guys do. It's not that much. It's the wave component itself that's expensive.
Right. Just the state vector of the wave. But the fact that you have so many variables flowing around.
Right.
Okay. Good. Is it the same in CESM? Because when we talked about the performance, there was actually a substantial factor of 10 difference between having spectral things on and off.
Maybe. I'm not sure I looked at those numbers, but again, we're doing 25 frequencies, but we're also running WaveWatch at 3 degree resolution. So maybe the frequency itself is a more significant cost than the 3 degree. But if we go down to higher resolution, then we're gonna, that's all gonna be lost in the noise, I think.
Yeah, I think all tests I've heard of is even if you go to a higher spatial resolution and reduce your spectral resolution, it doesn't help much. Like Greenlee tried back in the day, and it doesn't really, because at the end you have a 4-dimensional cube you have to get through this computer, right?
Right.
So, and the way how WaveWatch is structured, it's sadly the way how it is.
We'll solve the WaveWatch comparable problem eventually.
Give me funding, then I can.
Well,
Yeah.
Unfortunately, I haven't found the money tree, but I do. Dan, I saw your hand up a little bit ago.
Yeah, thanks. I wanted to mention the crocodile project, which we have here, which is really about making regional modeling in CESM much more accessible. So building Python front ends, starting with MOM6. So now we can kind of configure and run regional MOM6 pretty quickly. We're very interested in working with the CICE and CICE communities to include regional CICE capabilities. So right now we can run Pan-Arctic and Pan-Antarctic, but we brought on Dave this year really to develop things actually on the CICE side to enable more open boundary condition capabilities within CICE. So we're hoping to, so we have these annual workshops. The next one will be in September, October. I'm hoping that we might have some ability to run regional CICE there. And I don't know if you want to talk more about, I think that we're kind of downstream of some other developments within the CICE consortium in terms of these like ghost grid cells on the boundaries and stuff. But we're very interested in collaborating with you all on that.
So one question I have before we continue the conversation is Dan and I have talked about, the September, October workshop, if there's any interest within the more polar community of having a number of polar sea ice people come to this. So if the September, October workshop was a little bit more polar, there was a large group of us, how many people would want to come to that? Just a quick show of hands or think they could come that time of year. 70. Okay.
Yeah. Awesome.
Okay.
Awesome.
Okay. That's good. There's a lot.
And I will just add that Garant was at the, crocodile workshop earlier as well and had some really cool, regional Antarctic and Baltic Sea results and stuff like that. And we may actually highlight some of that this afternoon.
I know it's hard to plan.
Yeah.
In general right now, just with life, but.
Just to add to Dan's point, can you, how much effort is it to do crocodile with WaveWatch?
Yeah, Melissa was also just asking this question. In talking to Dave, that's also something that we would love to do. I don't know if it scales with the area of the domain or something like that.
Well, once you cut this down to a region problem around Antarctica, the computation it's way better because you don't resolve the whole globe.
Yeah.
Right, especially in a regular grid setting. So that cuts down the development costs for the parameterizations a lot.
Right, and so if that's a matter of staging, boundary, and initial conditions, we'd also be really interested in doing that.
Historic winds, so it's historic waves. So you can just prescribe the one in WaveWatch.
Cool.
Yeah, I wanted to go back to this. We were talking about like inner comparison, and I don't do much with waves. Actually, I mostly try to avoid ice with waves in it if I can. But I'm wondering, do we have the data to back up this comparison? Like, what is the, it's great to compare across the different models, but at some point, if you're trying to make a decision of what parameterization or simplification to go with.
You mean observational data?
Yeah, you need some sort of standard that you're comparing to. And if all the different studies are comparing to different observational products, that would be.
Yeah, I'm gonna say, Chris, I know at your summer workshop you talked about this, so go ahead and speak to it. Yeah.
The answer is we do have some global products. Me, Ed, and Alec actually wrote a paper developing a wave and ice product that Bhutan has used pretty successfully to do WaveWatch 3 coupled comparisons. So on the global scale, that's possible. And there's been some effort to, I think, look at regional information, maybe from Danny Dumont's work in where Canada. So I think there are some standardized data products, but again, it comes down to how you make the comparisons. And Guillaume wrote a paper in Proceedings article or Royal Society article a couple of years ago detailing how to do the global comparison between a couple model and this wave ISAT2 based data product.
Is it a follow-up? Erin?
Oh, it's related to this, yeah. So I think ISAT2 has something called freeboard, and so I would really love to be able to put a freeboard estimate into our models to have a more direct comparison to potentially freeboard measurements that come from satellite products. I think that would be a fun way forward to.
A history file.
Yeah, like something right out of the model, like instead of calculating thickness or something, have the model estimate what the freeboard is. And maybe we could compare more directly to ISAT2 freeboard. I don't know.
That is a standard CMIP variable
Is it?
now.
Okay.
Yeah, SIFB. I've
Okay.
implemented this in SICE and it will be part of our standard CMIP contribution.
I guess
we gotta do it too.
Gokhan, is yours on kind of the same topic of output, or is it a?
Well, go ahead, say, and then I'll.
Well, I was gonna say, I just wanted to, either you can say it out loud or come talk to us too, but necessary wave output for CESM or CMIP7. So we brought this up earlier, you know, CC was saying it'd be nice to have more wave fields. Those might not be default in CMIP7, which we think we are contributing to still, just that's the guidance right now, as we haven't been told we cannot. You know, are the, you know, significant wave height and wave period, are those the two main things we want, or is there anything else that we really need to make sure is output as a standard to understand, and I guess flow perimeter and those sorts of things are default, at least in CESM now. Is there anything else someone wants to put out there that needs to be like standard output in all the models?
I think there's the CMIP-rated call clips thing that organizes wave-rated outputs. Not sure if they care about the CI's components, but there should be standardization for that. It would be good to have a directional quantity.
Mm-hmm.
Right, so, and it shouldn't be much different than the things we should couple, I think, right? The stuff you get from the coupler should be a sufficient subscription of the spectrum.
Yeah. I do want to mention that within SICE, freeboard is calculated differently within different parts of the model. And so it's something to keep in mind with any of these comparisons. There's not necessarily like a single value. And there's reasons for that.
Yeah, going back to the output, I think the paper that Baylor and Patricia just wrote describes the wave fields that are required for CMIP7.
Okay.
I need to double check, but I remember that.
Okay.
Go
And then
for
for,
Baylor.
and I was gonna say for development simulations with CESM, like CC said, maybe we can have some other, you know, if we do some coordinated experiments that are coupled runs without wave extraction or with different wave fractures, we can have some extra output from MOM or something, even if that's not a CMIP variable. And we can just kind of get a list of those or something. Okay.
Yeah, so speaking of Baylor, I was going to bring up two things. The paper, that paper is apparently in revisions right now. And if, I think it's available, if you think that there is actually missing fields, I think that can still be incorporated during the revision stage. The second thing is that we had a meeting with him on Tuesday. He was keen on essentially bringing the theory wave model, and which will essentially supposedly eliminate all these costs. But I don't know how applicable that is under all of these things. And he was asking essentially when he can essentially start playing with the theory and Paul, right? Paul with CSM3 versions. So I think, I mean, I don't know, I'm just bringing it up because I don't think that anybody mentioned the theory waves, and that can essentially speed up things a lot.
Well, it doesn't propagate. It's a local model.
Yeah, it's probably local, but I mean, are there any applicable situations that can be used or not?
Everywhere but the sea ice.
And also the latest ocean parameterization relies on the Stokes velocity, which is not available.
Yeah, so there's now the discrepancy to the largest stuff. So there you have to whatever, I'm not that debate, but for the specific problem of wave propagating CS, you have to propagate the wave formation. That's what waves does not do. Right? So Pickles would do it. Otherwise you have to use spectrum mark. sorry for the plug. Yeah, so yeah, I think that's. But I think the plan is to have the three models exchangeable, like theory waves and WaveWatch, so that the theory waves runs as a component system in place of WaveWatch. So that's what Paul did, and I think it should be ready to use.
I think it's ready to use. They just want to test it, I think. Yeah.
They tested, not in couple, but in G cases. The thing is, our development CSM3 physics it requires fields that are not provided by the theory wave. So we could not go forward with that as is, unless we go back to the CSM2 vertical mixing physics, which we don't want to.
Okay, that seems to be another offline discussion.
One thing I wanted to point out, that Gustavo just mentioned G cases. I think we have talked at least offline about having these. So G cases are a fully active ice ocean, but we use atmospheric forcing. So we are interested in having some of these constrained simulations that you mentioned, Letty. So I think those will be something we coordinate on. And then we could use that to compare to, the observed historical periods. So something like that will be available that's cheaper than running the whole fully coupled system and stuff.
I'd say it'd be useful to add to that some nudged wind runs. So still fully coupled, but where we nudge the large scale circulation, because then you at least have some coupled interactions with the atmosphere.
Yeah.
So I think that would be a nice additional set of standard runs. And Ed agreed. He put up his thumb. I know, what a surprise. Someone who's not used these runs at all.
And Letty.
One thing that came up was the saving the MIZ directly as an output for CSM. There, maybe Chris has an idea, but because it's a length scale measure, how do you do that? Like, sounds a bit like a mixed layer diagnostic that varies on short time scales, but you want to save it as a monthly output. So you need to think about how to actually do that in the model, right? You understand what I mean?
Yeah. Chris, you had your hand up earlier too. I don't know if you.
Oh, that was about something different.
Okay.
I don't have an answer to Moni's claim that I have an answer.
Do you mean like size producing like a hemispheric mean MIZ quantity or something and defined metrics like that?
Yeah, right. So that would be like an online metric calculation, which is unusual, I think, in CSM.
Well, you have
so that you have to program that in the model while it runs, because you probably want like a mean, a max, or a min, or something like that.
Something like that, I would kind of prefer to do offline. So as long as we had daily output, would that be sufficient to get an estimate of the marginalized zone daily or something?
Yeah, that works for CSM probably not, but not for CMIP. I don't know.
Yeah.
I was just going to say, with all the discussion about maybe new metrics like an MIZ metric or observational comparisons, it'd be good to think about putting some of this stuff into like our standard Cupid diagnostics, which maybe is a longer term goal because we have to get CSM3 finished and all that. But I think it would be nice to have these in the standard diagnostics ultimately.
Yeah. We'll talk to, at least we'll mention Cupid a little bit this afternoon when we're the co-chairs are presenting after lunch. I do want to acknowledge that it's 10:33 and we didn't actually plan a break before this. And so some of you snuck out, but other of you might be like, I need to go. And there should be food and snacks out there. So I would encourage us all to take a break, continue talking out there. And then we'll come back here at 11 for Chris's seminar.
Can we see the comment that just came up?
Yeah.
I was something about, I think, modernizing WaveWatch 3 maybe.
Yeah, I think Hendrik has some plans. Yeah. But what's the time frame for that, Nick?
I don't know that exactly. But if there's things to work in, they can be worked in. I think that's worth noting.
Great. We will see you back in here.
The ice sticks up above this.